Hello and welcome to the lecture recording for Chapter 22, which will go over digital modulation. From Chapter 20, we went over the introduction to modulation, where you saw the benefits of using a carrier frequency. Some of those benefits were now that we can use smaller antennas. So back in the day, we had pretty large antennas on our cars to capture the AM and FM radio, but now we can use smaller antennas, not these large ones. The other benefit is now we're able to transmit signals over longer distances using analog signals. So in this lecture, we're going to go over the benefits of digital modulation. Okay. For a digital communication system, information that we wish to send from a transmitter to a receiver are just bits. Okay, those bits can be information that represent anything from ASCII characters on a Word document. They can be numeric values that represent samples from an audio signal, which you did in the Chapter 21 lab, where you did analog to digital conversion of the songs. And they can represent colors of pixels in a digital image. Okay, the information carried are the bits, but we don't actually transmit bits out. What we use is we transmit waveforms that represent those bits. So remember from Chapter 12, the physical layer, we typed in something on the keyboard and we saw this digital waveform readout on the oscope to represent ones and zeros, just like that. Okay, so what I mean by symbols is, so we have a low voltage here to represent a 0 and a high voltage here to represent a 1. So there's two different symbols that we're using here, low voltage and a high voltage. So we can term this by symbol rate. Okay, we also use what's synonymous with symbol rate is baud rate, or we can just call it what's the baud. Okay, baud is the symbol rate. Okay, we're usually concerned with how fast information is being transmitted, which is related to the symbol rate. Okay, the number of symbols per second being transmitted. So how do you calculate the symbol rate? Okay, what's the symbol rate? Well, it's just the inverse of the period of one symbol. So you can see for this particular symbol here to represent a digital 1, we can see the time it takes to transmit that 1 is 1 microsecond. See, the scale here is in microseconds. So to transmit that 1 bit takes 1 microsecond. So 1 over 1 microsecond is your symbol rate. Okay. In this simple example, the bit rate is equal to the symbol rate. See that we can represent a 1 in that same amount of time frame, that same time frame. So 1 over the period for 1 bit is the same time frame here. So 1 over 1 microsecond. Okay. In later examples in this lecture, we're going to get into more complicated waveforms where we might have more than 1 bit to represent, more than 1 symbol to represent bits. So we have the bit rate here. Bit rate is equal to n, okay, where n is the number of bits per symbol. Okay, so in this easy example, okay, m is the number of symbols. Okay, so in this easy example, we have a high voltage, and then right here we have a low voltage. Okay, so two different symbols. So if you take log 2 of 2, okay, we can represent those two symbols using 1 bit. Okay, either a 0 or a 1. Okay, we're going to get into examples where we might have 4 symbols. So log 2 of 4 equals 2. So we can use 4 symbols, and each symbol will have 2 bits represented per symbol. So we're going to get into more complicated signals there. Okay, so the bit rate would be the number of bits per symbol times your symbol rate. Okay, digital signal frequency spectrum. Okay, unfortunately, digital signals are not conducive or even practical for a wireless transmission. Okay, we can't just operate in a single frequency. Okay, everybody's out there if everybody's out there transmitting on a single frequency, would be talking over each other. Okay, so in this plot down here is a frequency diagram of a seemingly large number of random ones and zeros. Okay, as is usually the case in digital communication. Okay, in this frequency spectrum, the pulses would take the following shape during the transmission. In this figure, the largest frequency is at 0 hertz. Okay, the largest amount of information is sent, okay, the highest amplitude here is sent at 0 hertz. And at regular intervals, the frequency goes to 0 magnitude. Okay, so it goes to 0 magnitude here, and you can see how the amplitude is attenuating as we increase in frequency. And this does go to infinity. Okay. Notice where these magnitudes go to 0 is equal to the symbol rate. Okay, these are multiples of the symbol rate as we go to infinity. Okay, so in this example, if the symbol rate was 500 symbols per second, okay, the frequency content would be equal at 0 at 500. So this would be at 500 hertz. Okay, the next null, we call these nulls where the magnitude goes to 0, would be at 1000 hertz. Okay, the third null would be at 1500, and so on. Okay, so these happen at regular intervals. Okay, and the bandwidth of the signal, okay, what we do is we call it the null bandwidth. The null bandwidth, since the majority of our signal is here in this first lobe here, okay, since the majority of our signal is here, what we do, instead of just counting, we can't have unlimited bandwidth, so instead of just counting all these other repeating signals, we call it the null bandwidth, where we cut the bandwidth at the first null. So where it goes first, where the magnitude is first 0, that's where we're going to cut off our bandwidth. So in this case, it's going to be the highest frequency, f2, minus our lowest frequency, f1. Okay, if we simplify that, it's the symbol rate. Right here is 1 times the symbol rate, minus 0, right there. Okay, and that simplifies to being just the symbol rate. So the bandwidth of this particular symbol, or this particular signal, is the symbol rate. Okay. Digital modulation. Remember, in modulation, we want to carry the signal up to a carrier frequency. So this is the carrier frequency we want to bring that signal up to. See what happens when we have a carrier frequency. We not only have a right side, okay, this was the same waveform as we saw on the previous slide, but now we see the left side of that signal. Okay. Now the new bandwidth equation, when we carry a signal, when we modulate a signal, okay, the updated bandwidth equation is still the same. Okay, we take the highest frequency minus the lowest frequency, but in this case we're going to count the null on the right side and the null on the left side. Okay, so if I take the higher frequency, it's the carrier frequency plus the symbol rate, minus the lower side, we call them lower sideband. This would be the higher sideband, high sideband, or upper sideband. Okay, if I take the upper sideband here, minus the lower sideband, notice that the carrier frequency cancels out in this equation, and we're left with 2 times the symbol rate. Okay, this equation's important to remember, okay, for bandwidth. Okay, one way to remember this is, you remember from the previous slide, the upper sideband side is the symbol rate. And since when we modulate it, we now see the left side, so now we see 2 times the symbol rate. So we see the left side as well. So how do we represent a digital signal using ones and zeros with modulation? Okay, there's many different types of modulations. One type is called frequency shift keying. Okay, remember in a normal sine waveform, we have the amplitude times sine 2 pi frequency t plus the phase shift, some kind of phase shift. Okay, that's theta. Okay, so using shift keying methods, We can alter the amplitude, we can alter the frequency, and we can alter the phase, okay? Everything else remains the same in this equation. So for this first example, we're going over frequency shift keying, so we're going to alter the frequency here, okay? So frequency shift keying is a scheme in which the digital information is transmitted through discrete frequency shifts of the carrier frequency. Okay, so this was used back in the day when we used dial-up modems. So this lower frequency, 1070 hertz, equaled a 0 bit, represented a 0 bit. And the higher frequency, 1270, represented a 1 bit. So you can see down here, the frequency is the lower frequency for this time period here. Okay, so the lower frequency, that would be the example of the 1070 hertz. So the frequency of this waveform here is 1070 hertz. So that represented a 0. Then we increase the frequency. You can see here the frequency is increasing for this time period. And that would represent the 1270 hertz, which represented a 1. Okay, so this is one way we can modulate a signal just by altering the frequency. Notice the amplitude is the same throughout the signal. The amplitude is the same throughout this entire signal. And notice the phase is the same. The phase is not changing. The only thing that we're changing is frequency. Okay. Now, what does it look like in the frequency domain when we're calculating bandwidth? Okay. Some terminology here. The higher frequency component is called the mark frequency. Okay, so the higher frequency, let's say the higher frequency represents a 1 bit. The higher frequency is called F mark. Okay, and then the lower frequency is called F space. Okay, and since we're using two different frequencies, you see two distinct spikes here. Okay, so those are the two frequencies that we're shifting in between to represent a 1 and a 0. Okay, so the bandwidth equation for frequency shift keying is sort of the same thing that we did before, but we're going to take the null to the right of the F mark, the first null, okay, to the null to the left side of the lower sideband. So this is the null of the upper sideband, and this is the null, the first null to the left of the lower sideband. Okay, so how do we figure out that the frequency change from this null to this null? Well, we take F mark plus the symbol rate. Remember, the distance here from F mark to the first null is the symbol rate. So we have F mark plus the symbol rate minus F space minus the symbol rate. So the distance from here to here is F space minus the symbol rate. Okay. So F mark plus this is bit rate, but in this case bit rate equals symbol rate. So this is equal to our sim. Okay, this is also equal to our sim. Okay, so F mark plus the bit rate right here minus F space minus the bit rate here. Okay, so you can see if we simplify this down, F mark, it simplifies down to F mark minus F space plus 2 times the bit rate. Okay, so this to see that in action, we'll take this first component, so F mark, which is here, minus F space, which is here, so that's going to give us the frequency change between these two. Okay, plus 2 times the bit rate. So this is one of the bit rates, and this is the second bit rate. So that gives us the full difference in the spectrum here. Okay, so this is the bandwidth equation. This is another important equation to remember. This is the bandwidth equation for frequency shift keying. And if you go to page 456 of your notes, there's a list of all of the bandwidth equations for the different modulation types. This is just the first one we're going over, FSK. Okay, so here's a quick practice problem, 22.1. Okay, you have a frequency shift keying transmitter using an F mark frequency of 500 kilohertz. So this F mark is 500 kilohertz. Okay, and F space of 380. So F space is 380 kilohertz. Okay, and sending 10,000 bits per second, or 10K bits per second. How much bandwidth do you need for your transmission? Okay, so if you remember, from the peak here at F mark to that first null is your bit rate. Okay, and the peak here of F space to this null is also the bit rate. So we want to calculate the bandwidth. Okay, so we're going to take F mark, which is 500 kilohertz, minus F space. Okay, so that's going to give us the spectrum between F mark and F space. So that changed in frequency there. Okay, then we're going to add 2 times the bit rate because we need to account for this space here and this frequency change here. So plus 2 times the bit rate, and the bit rate is 10,000 kilobits per second. Okay, if you do this, you will get 140 kilohertz. Do this equation. 140 kilohertz. So the bandwidth required, needed to do this type of this signal, where you have 2 different frequencies. Okay, a lower frequency and a higher frequency. The bandwidth required to do this signal, we're going to need 140 kilohertz of spectrum. Okay. Another type of shift keying. We talked about frequency shift keying, but another type of shift keying is called amplitude shift keying, ASK. Another form of amplitude shift keying is called on-off keying, OOK. So amplitude shift keying, okay, if you remember the equation for sine wave, we have amplitude times sine 2 pi frequency t plus the phase shift. Okay, and frequency of shift keying, we altered between 2 different frequencies. Okay, so we use frequency shift keying here. This is used for FSK. For ASK and OOK, we're going to shift between amplitudes. Okay, we're going to alter the amplitude of our signal. Okay, so in this example here, we have a lower frequency, or a lower amplitude. Notice the amplitude is low here to represent a 0. Okay, and then a higher amplitude here to represent a 1. Okay, and this waveform continues on. Okay, notice the frequency is the same throughout this entire signal. The frequency remains the same as we go through the signal. The only thing that's changing is the amplitude. Okay, so we're only changing this value here to represent 0s and 1s. Okay, a simpler form of on-off keying, OOK, is called OOK. Okay, so we can have just 0 amplitude to represent a 0, and then some kind of amplitude to represent a 1. Okay, then it turns off no amplitude at all for a 0, then turns back on for a 1. Okay, this is better for error detection, because if you want to transmit a 0, okay, at the transmitter, if they're not receiving any voltage at all, they know that you're trying to represent a 1 or a 0, and they receive some kind of amplitude, some kind of signal, they know you're trying to transmit a 1. Okay, bandwidth for amplitude shift keying. Okay, so if you're looking at this type of signal in the frequency domain, okay, if you're looking at this in the frequency domain, you still have you're still brought up by the carrier frequency. Okay, remember this is repeated to infinity. Okay, so we're going to go to that first null on the left, the lower sideband, okay, and that first null on the right of the upper sideband. Okay, so the bandwidth for this is just going to be 2 times your bit rate, 2 times the bit rate. Remember the distance here distance here is your bit rate. Distance here is also your bit rate. So we have 2 times your bit rate. So this is the bandwidth equation for amplitude shift keying. Okay, we're going to sketch the on-off keying signal that represents the bit stream below. So here's a bit stream of 1s and 0s. Okay, the bit rate is 20,000 bits per second. Okay, the scheme here is we're going to have some kind of amplitude to represent a 1, and then since we're doing on-off keying, we're going to turn off, so no voltage at all for these 0s. Okay, and then we're going to turn back on for these 1s. Okay, so we're going to have some type of signal here to represent a 1. Okay, no voltage at all for the 0s. Okay, and then we're going to turn back on for 1, and then we're on again for another 1 bit. Okay. To complete this, notice the time scale here is in milliseconds. Okay, so if we're transmitting at 20,000 bits per second, okay, 20,000 bits per second. Okay, how many bits are we sending in 1 millisecond? Okay, so you can figure that out, do the conversion where you can see what the time scale is here for each bit. Okay, and phase shift keying. So again, I'll write the equation for signal. Okay, equation for a signal, we had amplitude times sine 2 pi times your frequency t plus phase. Okay, in FSK we change the frequency. In ASK we change the amplitude, and so in phase shift keying we're going to change the amplitude, or the phase term here. So PSK is a form of modulation where the carrier's phase is shifted. Okay. Binary phase shift keying, BPSK, has a carrier phase shifted between 1 or 2 phases. Okay, typically we use a 0 degrees phase and 180 degrees phase. Okay, so binary phase shift keying, meaning that we have 2 different, binary meaning 2, we have 2 different phases we're shifting between. And so in this example we had a 0 bit. Okay, so for 0 bit we have a 0 degrees phase. Notice that here it starts on the axes. Okay, and then when that symbol ends and we want to transmit a 1, notice that it has 180 degrees phase. It's 100 degrees out of phase, and it starts going negative here. Okay, now when we want to transmit another 0, notice that the phase then is shifted here. It goes from positive to negative. Okay, so the phase is shifting to represent these 0s and 1s. Okay, notice the amplitude is the same throughout this entire signal. Okay, the frequency is the same throughout this entire signal. The only thing we're changing is the phase shift. Okay, bandwidth for phase shift keying is the same as amplitude shift keying, where it's just 2 times your bit rate. Okay, here's a summary of the different shift keyings we've gone over. Okay, so in this is just your low frequency signal here. This is the signal that we want to send, the bit stream that we want to send. So here's your digital signal, digital readout of your signal. Okay, now if we wanted to modulate the signal using ASK, okay, so we're going to shift between 2 different amplitudes. Okay, notice here we have a low amplitude to represent the 0, and then a high amplitude to represent the 1. Okay, and that's just continued. The frequency is the same. The phase is the same. The only thing you're shifting between is your amplitude. Okay, and then another type of amplitude shift keying is on-off keying. So we have no amplitude at all for 0, and then we have some type of amplitude here to represent a 1. Okay, the other type of shift keying is frequency shift keying. So we had a low frequency. You can see here the symbol here has a low frequency to represent that 0, and then we increase the frequency here to represent a 1. Okay, a low frequency, and then we're higher frequency for 2-bit periods right there. Okay, amplitude is the same throughout this entire signal. Okay, frequency is changing, phase is remaining the same. The only thing we're changing is the frequency of the signal. Okay, and then the last one we went over, okay, BPSK. The B just means binary, meaning we're shifting between 2 different phases. So we're changing phase here where we have, looks like a 180 degrees phase here to represent a 0. And then we go to a 0 degrees phase here to represent a 1. And then back down to 180 degrees phase to represent a 0. And then a 0 degrees phase to represent a 1. Okay, amplitude is the same throughout this entire signal. Frequency is the same. The only thing we're shifting between is the phase. Okay, for amplitude and phase shift keying only, digital modulation schemes only, so we're not talking about frequency shift keying, we use something called a constellation diagram. Okay, so what a constellation diagram does for us is that it relates the output of symbols to represent in polar coordinates. Okay, so in this example here, we're going to go with a binary phase shift keying. Okay, binary just meaning we're shifting between 2 different phase shifts. Okay, so the radius from the origin here is your amplitude. So radius is the amplitude of your signal. Okay. And then your angle is your phase shift. Okay, so the radius here, whatever radius this is, that's the amplitude. Okay, and then starting with this phase, it's at 0 degrees phase, and phase increases as you go counterclockwise around this constellation diagram. Okay, so if you wanted to represent a 1, it would be at this amplitude, okay, at 0 degrees phase. Okay, in this scheme, if you wanted to represent a 0, okay, it would be at the same radius. Okay, notice the distance here is the same distance as here. Okay, these are equal. Okay, the same amplitude, but at 180 degrees phase. Okay, it doesn't matter where these symbols are located around the constellation diagram. Okay, notice that this is again another BPSK, just as long as if you have 2, okay, if you're shifting between 2 phases, make sure that they are 180 degrees out of phase. Okay, you want to make sure they're the furthest away apart as possible. So we can have a 0 here be this amplitude, wherever the radius this is, that amplitude at 90 degrees phase. Okay, and then a 1 can be the same radius, the same amplitude at 270 degrees phase shift. Okay. Okay, quadrature phase shift keying. So we had BPSK. When we had BPSK, we were shifting between 2 phases. Okay, Q stands for quadrature phase shift keying. So if you remember, quadrature means we have 4 possible symbols. We're shifting between 4 different phases here. Okay. Okay, so if we have 4 symbols now, remember M represents the number of symbols. Okay, so if we have 4 symbols, how many bits can we represent per symbol? So if you remember this equation here, log base 2 of M. So log base 2 of the number of symbols that we have, we're going to have 4. We're shifting between 4 different phases. Okay, log base 2 of 4 equals 2. So that means we can represent 2 bits per symbol here. So 2 bits per phase shift. So if you come down here to this first constellation diagram, notice I have 4 dots on here now. Okay, quadrature phase shift keying. The only thing I'm altering in this modulation type is the phase. Notice that if I want to represent 2 zeros, okay, it'll be at this amplitude, at 0 degrees phase. Okay, if I want to represent 0, 1, same amplitude at 90 degrees phase. Okay, 1, 0, amplitude at 180 degrees phase. Okay, and then a 1, 1. If I want to represent 2 1s, I can have the same amplitude at 270 degrees phase shift. Okay, again, it doesn't matter where you put these dots on your constellation diagram, as long as if you're doing 4 different phases, make sure that they are 90 degrees out of phase from each other. So here is a 90-degree angle. Okay, the difference in phase from 0, 0 to 0, 1 is 90 degrees. Okay, they're both at the same radius, so they have the same amplitudes. Okay, they all have the same amplitudes here, but they're all 90 degrees out of phase. Okay, a little difficult to see here, but you can see the difference. Okay, if we had, if we want to represent a 0, 0, you can see the different phase shifts that you may see. Okay, here's 0, 1 at 135 degrees out of phase. Okay, so these are what you would see for 0, 1, let's say. A 0, 1 is some type of amplitude at 135 degrees phase. This is 135 right here. Okay, so this would be the phase shift. Okay, all right. So since we're sending more bits per symbol, our bit rate is going to change now. Before, in our simple examples where we just had 2 symbols, log base 2 equals 1. Okay, if we had 2 symbols, we only represented each symbol using 1 bit. Okay, so as we increase the number of symbols, in this case we're going to use 4 symbols. So log base 2 of 4 equals 2 bits. So each symbol is going to be represented using 2 bits. Okay, since we're using more bits contained in one symbol, our bit rate is now going to go up. Notice the period for one symbol is the same, but in this period of one symbol, we're transmitting 2 bits. So our bit rate is going up by 2. Okay, so we're sending more bits quicker in the same amount of time. Okay. All right, so we have M-area modulation schemes where we're sending more than just 1 bit per symbol. Okay, this is another way of saying we're sending more bits, more than 1 bit per symbol. So the bandwidth equation for these M-area modulation schemes is 2 times the bit rate over n. If you remember, n is the number of bits per symbol. Okay, and this is very powerful. This is a very powerful way to modulate signals, because notice if we just stuck with 1 bit per symbol, let's say n is equal to 1, our bandwidth was 2 times your bit rate. Okay, now if we're able to represent a signal using 4 symbols, so if we're able to represent a signal using 4 symbols, we can now have 2 bits per symbol. And so now we're cutting that bandwidth in half. Okay, so we're able to send bits faster with less bandwidth. Remember in, I think it was in chapter 21, how expensive bandwidth could be. There's a portion of the spectrum that was auctioned off for $4 or $5 million. Okay, so to save on that bandwidth, what we could do is do this M-area modulation scheme where we're able to send more bits, okay, more bits per symbol. Okay, so here's a QPSK example in the frequency domain. We're calculating for bandwidth. Okay, this would be your bit rate. From here to there is bit rate. From here, the carrier frequency to this other null is bit rate. So 2 times your bit rate gets you this term. Okay, and then if we're able to send more than 1 bit per symbol, we're decreasing our bandwidth, okay? Because this denominator is getting larger and larger. We're able to send more bits per symbol. We're decreasing that bandwidth, okay? Here's an example of 8 PSK, okay? The number here represents the number of symbols. So in this case, we're representing 8 symbols. Here's what 8 PSK would look like on a constellation diagram. We have 8 symbols along this constellation diagram. Okay, notice the amplitudes are the same. The radius to each of these symbols is the same. Okay, the only thing that's changing is your phase shift. Okay, so this would be a phase shift of 45 degrees between each symbol. Okay, so if I have 8 PSK, how many bits per symbol can I send? So log base 2 of 8, meaning 8 symbols, okay, equals 3. So now I'm able to send 3 bits per symbol. Notice along this constellation diagram, I can now send 3 bits per symbol. Okay, so I just assign these symbols a 3-bit combination as I go around. Okay, so my bandwidth here, now it's even better. 2 times my bit rate, okay, divided by the number of bits per symbol, now divided by 3. In this case up here, I was dividing by 2. I cut the bandwidth in half. But now I'm using 8 symbols. Instead of 4 in QPSK, I'm using 8. Okay, 8 allows me to send 3 bits per symbol, which now decreases my bandwidth even more. This is great, great. The lower the bandwidth I need, the better. Okay. As in all transmissions, we're gonna have noise. This is inevitable. Okay, there's no way we can get away. Okay, as soon as a signal leaves the transmitter, noise is introduced to our system. So here's an example of a BPSK signal that's clean. Okay, this is a signal in a perfect world, is nice and clean. Okay, but once it gets to the transmitter, there's noise added to it. So you can see it gets a little messy. Okay. So here, here's the constellation diagram. This will be the constellation diagram for BPSK. Okay, I'm shifting between 2 different phases. Okay, the radius, the amplitude is the same for these 2 symbols. Okay, but the phase is changing. Okay, this is what it may look like to the receiver. Okay, we wanted to send, let's say, that symbol, but once it gets to the receiver, it may look like that. So it's up to the receiver to determine, okay, did they mean to send a this symbol right here, or do they mean to send this symbol right here? So they do a quick, distance calculation, and they know that if any symbol's close to this symbol right here, they meant to send this symbol. Okay. Likewise over here, if we wanted to send this symbol, but the receiver, it ends up looking like that, they do a quick distance equation. Okay, distance from there to there, okay, is shorter than there to there, so most likely they wanted to send that one. Okay, now it gets a little complicated, okay, as we add more and more symbols around the constellation diagram. So in this example, okay, instead of 2 symbols in this example, I now have 1, 2, 3, 4, 5, 6, 7, 8. So this would be an example of 8 PSK where I'm changing only the phase. Okay, it's a little bit more difficult for the receiver to determine what symbol they meant to send. Notice if I wanted to send this symbol, but at the receiver it gets picked up like that. Noise is added and it gets a little off. Okay, notice that the bounds of that symbol is 45 degrees, okay, or 22.5 degrees from that symbol. So each of these is 22.5 degrees of error on either side, plus or minus 22.5 degrees. Notice if that symbol falls outside of that range, the receiver is probably going to assume that this symbol, they meant to send this symbol instead. Okay, so we sent this one, but since it ends up here at the receiver thinks it meant to send that one. So this is where you get some bit error, which is bad in communications. Okay, so one way to fix this is here. This is just a slide showing that if you wanted to send this symbol, okay, this is a 16 PSK. On the previous slide, this was 8 PSK. So we're adding even more symbols around the same amplitude. Okay, so in 16 PSK, now you only have 22.5 degrees of error. Okay, to depict that symbol. Okay, or plus or minus 11.25 degrees either side of that symbol. Okay, so you can see as we add more and more symbols around this amplitude, around that circle, the chance of error increases. So one way to fix this is to use quadrature amplitude modulation. Okay, in quadrature amplitude modulation, we are able to represent a signal changing the amplitude and phase. Okay, in the other modulation schemes, we did one or the other. We either did some modulation using amplitude shift keying, or did some modulation doing some phase shift keying. Okay, QAM is the combination of amplitude and phase shift keying. Okay, so here's an example here of 8 QAM. So I have 8 different symbols, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I have, if I'm using 8 QAM, I have 2 possible amplitudes. So I have an amplitude here, and then I also have an amplitude here. Okay, it is a smaller ring is 1 amplitude, and this outer ring is the higher amplitude. Okay, so I'm shifting between 2 amplitudes and 4 possible phases. Notice that here's a phase, here's a phase, here's a phase, here's a phase. 4 different phases. Okay. The equation holds true for a number of bits per symbol, where we have log base 2 of 8. Okay, we're using 8 QAM. Okay, 8 QAM. Log base 2 of 8 is 3 bits. So 3 bits per symbol. Notice that I'm able to represent each of these symbols using 3 bits. Okay. And then here's what the signal would look like. Okay, if I wanted to send a 0, 0, 0. Okay, 3 bits of zeros. Notice 0, 0, 0 is right there. So it has the smaller amplitude at 225 degrees phase shift. So I know it's hard to see. It's hard for us to see that's 225 degrees out of phase. But trust me, at the receiver, it knows that that phase shift is 225. Okay, if we wanted to send a 001, notice 001 here is, again, a 225 degrees phase shift at a higher amplitude. So that's why it's the same phase shift as 000, but now a higher amplitude. Okay, if we wanted to send, one last example, 010. Okay, 010 is right here. Okay, so that's the lower amplitude at 315 degrees phase. Okay, so here's the lower amplitude. I know it's hard to see, but the receiver would be able to tell that that phase shift was 315 degrees. Okay. Notice that the time that we're sending here is still, the period is still a period of 1 symbol, but now since we're using 8 symbols, we're able to send 3 times the amount of bits inside that 1 symbol. Okay, and then we get some very complicated QAM signal levels. Okay, we can get up to 64 QAM. Okay, so we have 64 symbols in here. Okay, so we have different amplitudes. Okay, and then we also have different phases. Okay, to represent each of those symbols, and then 256. So there's 256 symbols within this modulation scheme. Okay, these are common in cable modems, satellite communications, high-speed, fixed broadband, wireless signals. So these are more sophisticated modulation schemes, and to us, it seems like it would be hard to determine the phase shift between here and here, but trust me, the receiver is able to determine that. Okay, once you get higher in QAM, let's say if we go higher than 256, then it gets a little bit more complicated. Okay. All right, last practice problem. Okay, using the signal constellation shown, or signal diagram over here, okay, answer the following questions. What type of modulation does this represent? Okay, so notice each of these symbols are at the same amplitude. So it's not amplitude shift gain. We're not changing amplitude. But notice that we are changing phase. So here's one phase of 0. Here's another phase. Here's another phase. So we're only changing phase. Okay, so this would be some type of phase shift keying. Okay, but we want to know how many symbols are we changing in this phase, or how many symbols do we have in this phase shift keying? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this would be called a 16 PSK. 16 symbols. Okay, number of symbols. And then PSK is the type of modulation we're using, modulation type we're using. Okay, how many symbols are represented? Okay, we counted around. We found that there are 16 different symbols. Okay, how many bits per symbol are being used? Remember this equation, log 2 of m equals n. We're trying to find n. So log base 2 of the number of symbols, we have 16 symbols, okay, equals 4 bits. So 4 bits per symbol. So each of these symbols can represent 4 bits. So this one right here, I would assign 0, 0, 0, 0. This one could be 0, 0, 0, 1. This could be 2. This could be 3, okay, and so on. Okay, what's the baud rate? Okay, remember baud rate is the symbol rate. Okay, it says if the baud rate, remember baud rate is symbol rate, so 10,000 symbols per second. What is your bit rate? Okay, so we have 10,000 symbols per second. Okay, and we want to find bits per second. Okay, so what do we need to multiply in order for symbols to cancel out and to have bits in the numerator in our answer? Okay, so I want to know how many bits I have per symbol. And we found that out up here. We have 4 bits per symbol. So I'm going to multiply that by 4 bits per symbol. And notice now the symbols cancel out. Okay, and you're left with bits per second. Okay, so 10,000 times 4. 10,000 times 4 equals 40,000 bits per second, or 4 kilobits per second. Okay, would 16 QAM be more or less susceptible to noise than this type of modulation? They're meaning, okay, instead of 16 PSK, is it more or less susceptible than 16 QAM? Okay, remember with QAM, we're able to alter amplitude and phase. Okay, so instead of having 16 symbols around the same amplitude, different phase, I can now represent the same signal using 2 different amplitudes and 4 different phases. Okay, so I'm spreading the goal here is to spread these dots far apart so the receiver knows which symbol you're trying to transmit. Okay, so 16 QAM allows me to separate those dots even further. Okay, separate those dots even further, so this is better to reduce noise. So would 16 QAM be more or less susceptible? Okay, 16 QAM would be less susceptible to noise, okay, because these dots are more spread apart than here. Okay, so that concludes chapter 22, digital modulation. Okay, stay tuned for security exercise 22.